Hello everybody, we're going to talk about some function properties that we want to look at when we see a function. One of the most important items about a function is its intercepts. And if you see a graph, it's really easy to point out where the intercepts are. So something curves through like this. All you have to do is circle those points where it crosses the x-axis and the y-axis. And this would be the y-intercept, and this would be the x-intercept. So it's really easy to see on a graph what those are. Now when you're given a function, for example, f of x equals 3x plus 2, and you're not given the graph, you could draw the graph and estimate the intercepts, or you could find out where is the x value equal to 0, because that's exactly what the y-intercept is when the x value is equal to 0, you are at the y-intercept. So you could plug 0 in for this and find out that, well, 0 times anything is 0, and you get f of x is equal to 2. So the y-intercept here would be 2, or the y value would be 2, or f of x would be equal to 2. And then the way you find the x-intercept is when the function value is equal to 2, right? So when f of x is equal to 0, or I'm sorry, yeah, when the function value is equal to 0. So you have 0 is equal to 3x plus 2, so I would have to subtract 2 to the other side and divide by 3, so I think it would be equal to negative 2/3. Okay, so that's a way you can think about intercepts both in the graph and seeing the function. Is when the x value is equal to 0, you find the y-intercept. When the function value is equal to 0, you find the x-intercept. Okay, increasing and decreasing is important. You see this, it's just an observation about a graph or how the values are changing as you increase your x. So this graph right here, it's increasing. The values of the function are increasing as you're going along to the right. It's just like reading a book. You're always going to the right, and if the values are increasing as you go to the right, you say the function is increasing. And then at some point around here, then it starts to go down, and then we say the function is decreasing. And then some point around here, it turns again, and now we say the function is increasing. So we can talk about that in terms of how it's concave and convex and going up. And so that's just the important part, is noticing where your function is increasing, where your function is decreasing. And then that also comes into that is the relative maxima and minima. So that same function, we'd say at this point where it turns, this is the maximum value that it gets to in this region, right? So it's relative to this part of the graph. We say this is a relative maxima, or it's a relative maximum. Maxima is a plural, right? Relative maximum. And then we see at this point it's as low as it gets in this portion of the graph. So we say that's a relative minimum. And I won't write it out, but the absolute maximum, it looks like it probably is infinity, like it will continue to go up. So there is no absolute maximum in this graph, and the absolute minimum, it looks like it would go much lower than this down here. It could probably go to negative infinity. But some graphs have an absolute maximum or minimum, like this one, for example. It's going to continue to go up in that direction and continue to go up in that direction. So the absolute minimum that this graph will hit is right there. It's also the relative minimum and the absolute minimum. Okay, another thing to notice about functions is their shifts. So there are certain patterns of graphs that we've gone over, and we'll go over some more. But if you see a graph like this, for example, you can say, oh, it looks like this thing was kind of shifted over and up. If I wanted it to be, nice and symmetric and centered on this 0, 0, it was shifted over and up. So we're going to talk about shifts a little bit more in detail and how we see them in the equations in the next video. But just recognizing that, oh yeah, it is shifted over, or if you had a circle you'd say the center is kind of it's shifted this way and that way, right? Or it could be down, right? It could be shifted down, for example. Okay, and this is not a function, by the way, it's just an example of shifting. Domain and range. Domain and range just talk about domain is the possible x values. It's like I live in this domain. Oh, domain. I live in this domain, so it's kind of like here's my stuff, right? And then range is like call a mountain range, right? It's like how high or how low is it? So this is the possible x values. And this is the possible y values or possible function values. So many times we will get functions that are limited that can't be in a certain area. So like with this kind of thing, we have what's called an asymptote. So it appears that this value right here, when x is equal to 0, does not work. So we might say all x values work except 0. So we say x is not equal to 0 in the domain. Also, it looks like in the y range that y could not equal 0. So the domain x is not equal to 0, and the range y is not equal to 0. Sometimes we have a graph just like this, right? And it appears that all the x values are possible. Like as we spread out, there are function values. You know, if I went way over here, it would be way up there, but there would be some value. So we'd say all x values are within the domain. So x is maybe say you put set notation with these curly braces and say all the reals. And then the range, we'd say, well, it has the y value. It can't go any lower than this, right? So whatever this value is, we'll call it a c. Y must be greater than or equal to c. That would be how that range would be limited. So that's a few of the things that we want to notice about functions. We want to notice their intercepts. We want to notice if they're increasing or decreasing. We can notice their relative maxima or minima, how they're shifted, and what is the domain and range, those possible x values or possible y values for the function.